In today's video, we're going to talk about absolute convergence. Here we have a series of negative 1 to the n over 2n. It's an alternating series, and here are the first terms as n goes from 0 to infinity. We have 1 minus 1/2 plus 1 over 2 squared minus 1 over 2 to the third, and so on. Now, if we add all of them up to infinity, the sum is going to be 2/3. If we rearrange the terms, we take the original terms and put them in some different order. 1 plus 1 over 2 squared minus 1 over 2 to the first plus 1 over 2 to the fourth. And these are the same terms, but they're out of order now. We're going to get 2/3 for this series. Now, when that happens, this series is said to be absolutely convergent. No matter how we rearrange the terms, we're always going to get the sum of 2/3. In some series, for example this one, an alternating series of negative 1 to the n minus 1 over n, here are the terms listed in order as n goes from 1 to infinity. And the sum is going to be the natural log of 2. In this particular series, if we rearrange the terms in this particular order, 1 plus 1/3 and then minus 1/2, and then add 2 positives and then add a negative and then add 2 positives and add a negative. If we repeat in a pattern like this, the sum is not the natural log of 2. It's not the same. It's actually natural log of 2 squared of 2. This series is only conditionally convergent because if we rearrange the terms, we don't necessarily get the same sum, even though the terms are exactly the same. Here we have the theorem: if the series, the absolute value, if this converges, then the original converges, which is nice. So now we only have to have one test if the absolute value converges. Then we say the original series is absolutely convergent if the absolute value of a sub n converges. Now let's say that the absolute value of a sub n diverges. We still now have to look at the original series, and if the original series converges but the absolute value diverges, then we say the original series is only conditionally convergent, which means if we rearrange the terms, we might get a different sum. In our example, we determine whether the given alternating series converges or diverges. If it converges, determine whether it is absolutely convergent or only conditionally convergent. So now we can take the absolute value of the original series, which turns all of these negative ones into positives. So this is going to be 1 over just the square root of n, which is 1 over n to the 1/2. And by the p series, p is less than 1, so this one diverges. Well, now we have to test the original series, and we do the alternating series test. So we have the limit as n approaches infinity of 1 over the square root of n, which is equal to 0, which is exactly what we want. And now we just have to show that 1 over the square root of n plus 1 that's a 1, is less than 1 over the square root of n. Well, if we add 1 to n, this denominator is going to be larger than the one before, which means this sequence is decreasing, which now this series passes the alternating series test. So the original series converges, but only conditionally. The absolute value diverged, but the original series converges, so the series converges conditionally. Let's look at the next example. We're going to take the absolute value of the original function, and then all of those negative ones become positive. So we have 1 over 3 to the n. This is a geometric series where a is 1/3, and r is also 1/3, which is less than 1. So this converges by geometric series. Now we have to, well, since this one converges, we don't have to look at the original. We now know the original one converges, and so our series converges absolutely.